Okay, this is our second lecture and the beginning of our discussion of linear algebra, which will last this and next week. Okay, the main ideas here are learning about matrices, about Gauss-Jordan elimination, how to operate on matrices, and how to invert them, okay, which will all be different ways to solve sets of equations. Okay, so our problem of the week this week is a little more of an algebraic problem. And again, it's not a complicated one, but I'm going to show you a couple of different ways to tackle it just so you have a handle on these different methods and how they work together. So just the problem is to solve this using both Gauss-Jordan and inversions. The set of equations 2x minus 3y equals 6 and x plus y equals 0. Okay, so let's kind of start off at the beginning, which is, I guess, always a good place to start. Defining what a matrix, okay? And those of you who have done any kind of coding are probably familiar with these because one of the important functions of matrices is in building codes to solve sets of equations, which is also why it is important to use specifically in this class as well as generally in this program, because it's something that you're going to use later on when setting up codes to solve much more complex systems than this. But as always, it's very good to start off with the simplest cases. So a matrix is a rectangular array. The size is given by the number of rows times the number of columns. So if you have obviously 3 rows and 2 columns, it's a 3 by 2 matrix. Okay, and as I mentioned, one of the important uses is for solving much larger and more complex systems of equations. Okay, so how do these work? Okay, so starting from the beginning, and this example will look familiar because you just saw it a few slides ago. So we have 2x minus 3y equals 6 and x plus y equals 0. Okay, so the way we do it is we strip away all the x's and y's and we just write the numbers, making sure they're lined up correctly. Okay, and this, as I mentioned, is called an augmented matrix because it includes the variables and the constants. Okay, and by the variables I mean the numbers that are connected to the variables. Okay, so this is an augmented matrix, 2 rows, 3 columns, so it's a 2 by 3 matrix. Okay, and completely reasonable to ask the question why we are bothering to do this. And the reason is once you have it in matrix form, you can do a lot of different operations to simplify it. And again, this is relatively trivial when you have a 2 by 3 matrix, but when you have something like a 200 by 300 matrix or something crazy like that, it becomes a lot more complex and you need to get a lot more regimented in your approach. Okay, so basically you have 3 different things you could do with matrices. You could interchange rows, you can multiply or divide an entire row by any non-zero number. You can but again, that has to be the entire row. And once you do that, once you multiply or divide by a non-zero number, you can add or subtract that from another row. Okay, so it's kind of 3 intertwined things you guys can do with matrices. Okay, so let's look back to the example here. And you'll see the notation that I use here. It's very important to be careful with your bookkeeping when doing matrix operations, because you will make mistakes doing this, and if you're really careful with your bookkeeping, it's pretty easy to go back and see where you made your mistake. Okay, so the first thing I do here, and again, the goal in matrix operations is to get zeros wherever you can. In the most simplest term, that's what you're trying to do. So here you're replacing row 2 by 3 times row 2. Okay, so instead of 1, 1, 0, we have 3, 3, 0. And applying that second rule, we can add our new version of row 2 to row 1. And why are we doing that? We're doing that because it's getting rid of a number and turning it into a 0. Okay, so row 1 is replaced by row 1 plus row 2. Okay, and at this point, to have a 0, you can kind of go back to the original algebraic equation and look at what you have here. So that gives you 5x equals 6 and 3x plus 3y equals 0. So you can fairly easily get the solution. Okay, and now the question maybe pops into your head, is there a less ad hoc way to do this? And we had kind of discussed that last week. And there is. Okay, the goal of really solving matrices is to get ones along the main diagonal. Okay, and the main diagonal is defined as first row, first column, second row, second column, third row, third column, etc., etc. So it's a diagonal going from the top left to the bottom right. So you want to get ones in that, and you want to get zeros everywhere else. Because once you've done that, you can read off the solutions. So if you look at that example at the bottom of the page, the solution would be x equals c, y equals f. That's all you need to do. Okay? Again, a little easier said than done, but once you get it in that form, it's a beautiful thing. Okay, so with the last example, let's kind of pick up where we left off there. We had 5, 0, 6 and 3, 3, 0. Okay, so now if we wanted to get it down to the identity matrix, which again is ones across the main diagonal and zeros everywhere else. Okay, so let's get rid of that 5 and turn it into a 1, and we do that. Okay, a little bit out of order from what I have on the page, but if you'd done that first, you would take the first row divided by 1/5 of the first row, gives you 1, 0, and 6/5. Okay, ignore that typo, please. And the second one, if we had divided that by 3, that would give us 1, 1, 0, and then subtracted out that first one, that would give us 0, 1, 6/5. Okay, again, that's kind of the reverse order of what I did on the page, but you can see it both ways. And this is also a good time to explain to you that there are definitely more than one ways to get from point A to point B here. Okay, you could all get there. I wouldn't say all, but a lot of you could get there in completely different directions and still not be wrong with the approach. Okay, this is very results oriented, so it really matters what you get to at the end. At the end, you want the ones across the diagonal, the zeros everywhere else, and you should all have the same solution. Okay, and this approach is known as, and sorry again, by the way, it should be 1, 0, positive 6/5 in the first row. This approach is known as Gauss-Jordan elimination, okay, named after the famous mathematician Carl Gauss and some guy named Jordan. Okay, so this is a very formal approach to solving any kind of matrix problem. Okay, you started off kind of with a simple example, but we can really go kind of crazy and use it for any number of rows and any number of columns. Okay, so let's try a slightly more complicated example, which I have here. Okay, so again, go from the equations to the matrix, and this is a really, really common place to make mistakes. Okay, do not make a mistake here, because one of the most frustrating things you can do is miss a minus sign, add in an extra minus sign. As you can see, I make plenty of mistakes myself. But if you make a mistake in the beginning, you could do a lot of great work and your solution will be totally meaningless. Okay, so double and triple check that your equation, that your matrix matches the equations, both with the numbers and with the signs. Okay, so if you're comfortable, then you want to go ahead and start the Gauss-Jordan process. Okay, and again, try to get zeros in the places you need them. That's a great place to start. Okay, so as I mentioned a few moments ago, there are lots of different ways to get from point A to point B here. My own approach, you could see on the page, the first thing I did is I replaced row 2 by row 2 plus row 3, because that gives us a 0. Then I replaced row 3 with row 3 plus twice row 1, because that gives us another 0. Okay, if you can get 2 zeros in the same column, that's really a good approach, a good solid way to do these. Okay, so next, replacing row 3 with row 3 plus thrice row 2 gives us another 0. And the third row, as you can see, is almost down to identity. If we divide it by 13, okay, we have our 1 in place. But it's in the wrong place, it's in the wrong row. Okay, we need 1s in the diagonal. Okay, so we need that 1 to be in the second row, not in the third row, because it's in the second column. Okay, so if we switch those guys up, okay, row 2 is done, and now we can use row 2 to simplify the other rows. Okay, and you can kind of see what we're doing here. I will give you a second to read what's going on. Okay, so we are almost there. Okay, we want to let row 1 equal the -1 times row 1, which again is totally permissible. We can always multiply or divide an entire row by a non-zero number. Okay, one more step and we have an identity matrix. Okay, and this is a beautiful thing because you need to do nothing else. You can just read off the solutions. X equals 1, y equals -1, z equals 3. Okay, and as I mentioned before, and I'll mention again and again, the key to this approach and to matrices in general is just really, really careful bookkeeping. You're most likely not going to make mistakes in basic arithmetic. You're going to make mistakes with your bookkeeping. So just be really careful with that. And of course, that leads to the question, do we always get these really nice textbook problems with an answer that looks so lovely? The answer is no, we don't. The real world is a scary place. So if you look at this one here, and this is kind of a ... yada yada yada, you get to the final form here, and you have a row of zeros. Okay, what that means is that first row is no longer of use to you. It doesn't tell you anything. So what you're really left with are 2 equations and 3 unknowns. And what does that tell us? Tells us that it's an inconsistent set of equations. Okay, so you really have to be aware of that possibility because it will happen. Okay, so going back to matrices in general, there are a lot of correlates between regular numbers and matrices. One of them is addition, another is subtraction. If you want to add matrices, all you have to do is term by term add them together. If you want to subtract matrices, same thing, just term by term. And again, it's just bookkeeping. Make sure you are adding the row 1, column 1 to the row 1, column 1 of the second one. Okay, and clearly this will only work if the matrices are the same size. Okay, multiplication of matrices. If you're multiplying a scalar, which is a regular number, times a matrix, all that means is that you're multiplying each number in the matrix by that number. Okay, same thing with division. Okay, you can multiply that by 4, you can divide it by 4, it doesn't matter. It's going to give you either an expanded or contracted matrix. Okay, if you're multiplying by a number, you're expanding the matrix. If you're dividing by a number, you're contracting the matrix. Okay, things get a little bit hairier when you're talking about multiplying a matrix times a matrix. Okay, and this only works if the number of columns of one matrix equals the number of rows of the other. Okay, so you cannot multiply a 2 by 2 by a 3 by 3. You can multiply a 2 by 2 by a 2 by 3, or a 2 by 2, or a 2 by 10, or a 2 by 100. Okay, as long as the number of columns of one matches with the number of rows of the other, you can do that. Okay, and this is the process. Okay, so we have a 2 by 2 multiplied by a 2 by 3, so that is doable. Okay, and this is kind of a long process, but you're multiplying the rows of the first times the columns of the second. Okay, and also one thing to notice is that the number of rows of the first and the number of columns of the second that will give you the size of the matrix you're going to get at the end. So a 2 by 3 times a 2 by 2 is going to give you a 2 by 3. A 3 by 3 times a 3 by 5 is going to give you a 3 by 5. Okay, so it's always going to give you the same size as the second thing you're multiplying. So hopefully that makes sense. Okay, but just I kind of started the process here with this example. So you take the first row times the first column, the first row of the first times the first column of the second. Okay, and that gives you a number, which is going to be the first row, first column of the new one. You take the first row times the second column, it's going to give you the first row, second column of the new one, etc., etc. Okay, so you have to do this 6 times to get the 6 different pieces of the matrix. Okay, and this might seem like a lot of busy work, but there is a good reason for this. Okay, and that reason is matrix inverses. Okay, and again, I'll pause here for a second to tell you that a lot of this kind of grunt work will be done by the computer, but it's always important to understand where this stuff comes from. Okay, don't want to treat the computer as a black box. Okay, so the reason we're doing this is kind of, you can see in the example I give you here. If you're solving the algebraic equation 2x equals 6 and you want to solve that for x, okay, it's a pretty simple process. You divide both sides by 2, you get an answer of x equals 3. With matrices, it just does not quite work that way. Okay? Instead of dividing by something to solve for a matrix, you have to multiply by the inverse. Okay, so let's look again at our favorite example here. 2x minus 3y equals 6 and x plus y equals 0. Okay, so in a more traditional algebraic sense, if we had broken this up into numbers times variables equals a solution, this is what it would look like. Okay, so we can really think of this as, if we think of that first matrix as A, the variables as x, and the second as b, we have ax equals b. Okay, so this looks more like a typical algebraic problem. And if this were just regular old algebra, we would say x equals b over a. But this is not regular algebra. So the actual solution to that is going to be x equals a inverse times b. Okay, so just understand the connection between solving an algebraic problem and solving a matrix. Okay, it's kind of similar, but not exactly, because you can't just divide by the matrix. You have to multiply by the inverse. Okay, and the way we find the inverse is by realizing that any matrix times its inverse is going to give you the identity matrix. Okay, so the way we set this up is any matrix, okay, our matrix here, times its inverse, okay, and we're going to call its inverse x, y, z, w. I guess I could have done that in actual alphabetical order, but whatever. And we're going to say that any matrix times its inverse is going to equal the identity matrix, okay? So we're going to set this guy up, as you can see on the page. The matrix times its identity is going to have to equal the inverse. So matrix times the identity is going to be the inverse. Okay, so if you go ahead and plug through here, what you are going to find, okay, and our goal, sorry, I just want to give you guys a second to read this page. Okay, it is a little bit confusing, but basically, if we can flip-flop the identity with the matrix, it's going to give us the inverse. Okay, and again, I assure you this is nothing that you'll have to do manually, but just have a quick understanding of how it works. Okay, so if we do our magic, our Gauss-Jordan, what we're going to end up with when we flip things around is the inverse matrix, which is 1/5, 3/5, -1/5, -3/5. And we can get our solution by multiplying the inverse times the right-hand side. Okay, multiplying that out using the methods that we learned a few slides ago, and that gives us a very familiar looking solution. Okay, 6/5, -6/5. Okay, so we kind of rehashing, we solved that equation using Gauss-Jordan, and in a little more gory, not so much fun way, we used matrix inverses. Okay, and again, and I cannot repeat this often enough, the matrix inverse approach is nothing you will need to do by hand, but I really just wanted you to understand where it came from. So now that you've done that and you understand it, then you're in good shape and you won't have to worry about it again. Okay, and just a couple of words before I leave you until the next lecture. You can only invert square matrices, okay? Which is fine because a lot of the stuff you will be dealing with will have as many, as we mentioned before, if you don't have the same number of equations as you have variables, then you can't get a unique solution anyway. So any set of equations that has the same number of equations as variables is going to be a square matrix by definition, okay? But not every square matrix has an inverse, okay? So if you can't invert it, it means there's not going to be a solution, just so you know. Things like that do happen, and you shouldn't think it too crazy when they do. Okay, so next week we will dive further into matrices, and I will see you then.